Assalamu alaikum everyone. I am Nusrat Jahan Raina. Today I will present DLC OBE assessment. Here we can see in question number 1 the block diagram. Here the block diagram we can see that the system starts with an entry sensors and an exit sensor. These sensors feed into an up-down counter. The diagram shows that the counter's output representing the current count is labeled as A. The counter's output A is connected to register 1. Another input to the system comes from a keypad which is connected to an encoder 4 into 16. The output of the encoder is connected to register 2. Register 2 holds the value representing the maximum space or capacity, which is labeled as B. The output from register 1A and register 2B are fed into a comparator. The comparator has three possible outputs, which is A greater than B, A less than B, and A equal B. The output of the comparator control the display logic. If A greater than B, it triggers a 555 timer astable circuit which controls a 7-segment display labeled full. If A less than B, it triggers a circuit to show a space available using a 7-segment display. If A equal B, it triggers a 555 timer monostable circuit which also controls the full display. There is also a connection shown from A equal B to a show input for the 7-segment full display. There seems to be a connection from both A greater than B and A equal B to the full display, potentially indicating different display behaviors. So in next slide we can see the flow diagram. Here the process starts with start system. Next the maximum space is set with the keypad. This corresponds to setting the value stored in register 2 from the block diagram. The system then initializes the counter to 0. This corresponds to clearing the up-down counter. The flow enters a loop constantly monitoring the sensors. If an entry road sensor detects a card, the counter is incremented. The flow then proceeds to compare box overall count with the maximum limit B. If A is equal to or greater than B, the system displays full. If A is less than B, the system displays space available. After displaying the status, the flow returns to monitoring the sensors. If the entry road sensor does not detect a card, the system checks the exit sensor road. If an exit sensor detects a card, the counter is decremented. The flow then proceeds to compare box overall count A with the maximum limit B, following the same comparison logic and display outcomes as after an entry. If neither sensor detects a card, the system continues to monitor the sensors indicated by the arrow looping back. Here we can see in the next slide 4-bit synchronized up-down counter is explicitly stated to be used for the entry and exit sensors. It is described as synchronous, meaning that the state changes are synchronized to a common clock signal for inferred from diagram showing a single clock input to all flip-flops. The counter is designed to perform two operations, up incrementing and down decrementing. The operation up or down is controlled by external signals or logic as shown in the equations and the sequence table. The counter is implemented using 4 JK flip-flops. The diagram on this page, we can see that four flip-flops labeled as FF0, FF1, FF2 and FF3, each with J and K inputs and Q outputs, Q0, Q1, Q2 and Q3, commonly associated with JK flip-flops. The sequence table on uh, previous page, we can it shows the binary output states Q3, Q2, Q1, Q0 for decimal counts from 0 to 15. It indicates how the state changes when the counter is commanded to count up or down. For instance, starting from state 0 and up command moves to a state 1001, and a down command from a state 1 moves back to a state 0. Here we can see the equation for the J and K inputs of the flip-flops. This equation defines the logic required to make the counter count up or down based on the current state Q0, Q1, Q2, Q3 and the up-down control signals. For example, J0 is equal to K0 is equal 1. This means the first flip-flop FF0 toggles its output whenever the clock edge occurs. Here J1 is equal K1 equal Q0 into up plus Q0 bar down. This equation for FF1. Here J and K inputs shows that it toggles if Q0 is high and the up signal is active, or if Q0 is low and the down signal is active. The equation for J2 or K2 and J3 and K3 become progressively more complex depending on the previous flip-flop states. Q0, Q1 for FF2, Q0, Q1, Q2 for FF3, and the up-down control signals implementing the standard logic for a binary synchronous up or down counter. The outputs of these flip-flops Q3, Q2, Q1, Q0 represent the 4-bit binary count. This output represents the current number of entries minus exits. Here we can see two 555 timer circuits. One 555 timer is triggered by the A greater than B output from the comparator. This timer is labeled as being configured in astable mode. Its output is connected to a 7-segment display labeled show. The other 555 timer is triggered by the A equal B output from the comparator. This timer is labeled as being configured in monostable mode. Its output controls a 7-segment display labeled full. The diagram shows the standard pin connections for a 555 timer. Pin 1 ground, pin 2 trigger, pin 3 output, pin 4 reset, pin 5 control voltage, pin 6 threshold, pin 7 discharge, pin 8 VCC. For the astable timer, resistors and a capacitor are shown connected to pins 7, 6 and 2. For the monostable timer, resistors and a capacitor are shown connected to pins 7, 6 and 2. There are calculations presented related to finding values labeled P frequency duty cycle using given numbers like 2, 5, 6, 7, 1, 2, 6. It appears to calculate a frequency of 10 Hz and a duty cycle of 64%. Here we can see that it uses the calculated frequency from the previous page to find the total period time. It then calculates the high time TH and low time of the astable output pulse based on the duty cycle. TH is equal duty cycle into T. which we can get 64 ms, and TL is 1 minus duty cycle, which we get 36 ms. The page uh, shows calculations and determine the values of resistors R1 and R2 used in the stable 555 timer circuit using a given capacitor value C, 250 microfarad, and the standard 555 timer equations for TH and TL. The calculation for R1 plus R2 uses the TH value and the capacitor value. The calculation for R2 uses the TL value and the capacitor value. Based on these calculations, R2 is determined to be approximately 207.79 ohms, and R1 is then calculated by subtracting R2 from the sum. The calculation results in R1 being approximately 161.62 ohms. This calculation show how the required timing characteristics for the stable mode 555 timer, which drives the show display, are used to determine the necessary resistor values when the capacitor value is known. The show display connected to the stable timer's output would likely blink at the calculated frequency and duty cycle when the count A exceeds the capacity B. Here we can see a state diagram and a state table. The state diagram depicts a sequential circuit with different states represented by circles containing a 3-bit binary code, 001, 0, 000, 001, 010, 011, 100, 101, 110, and 111. Transitions between states are shown by arrow labeled with inputs A or B that cause the transition when the clock edge occurs. The inputs are labeled A and B on the transitions. There is also a reset input that takes the circuit to the 000 state. The diagram includes annotations like if TH is greater than 4 and TL is greater than 4, suggesting that inputs A and B might be derived from timed signals, possibly related to sensor pulses or timing signals. The clock period is given as 1 ms. The state table lists the present state, PS2, PS1, PS0, and the clock input, the next state, which is NS, NS2, NS1, and NS0, and two output signals A and B. The table details how the circuit transitions from a given present state to a next state upon a clock edge, based on inputs through inputs A and B are shown as outputs in the output column, which appears to be a labeling convention in this context, the where A and B might be the outputs of this specific state machine controlling something else. For each state transition row, and the corresponding output values for A and B are also listed. For example, in the state 000 upon a clock edge, the next state is 001 and the output are A is equal to 1, B is equal to 0. Here we can see output equations for the signals labeled A and B from the state machine described on previous page. The equations are derived from the state table using the present state bits PS2, PS1, PS0. The equation for output A is initially written as a sum of product terms corresponding to the states where output A is 1 in the state table. This equation is then simplified algebraically. The simplified equation for output A is given as A is equal to PS2. Similarly, the equation for output B is written as a sum of product terms corresponding to the states where output B is 1 in the state table. This equation is also simplified. The simplified equation for output B is given as B is equal to PS2. Here we can see the Verilog HDL code, likely implementing the state machine defined on previous pages. The code defines a module named TLC binary. It has inputs clock and reset and outputs A and B, internal signals PS state, present and an state means next state are defined as 3-bit register, and always uh, block is used to update the PS state register with the N state value on the positive edge of the clock. This is typical behavior for the state register in a synchronous state machine. The Verilog code is also includes assign statements for the outputs A and B, linking them to the bits of the PS state register. Based on the assign statement, output A is assigned the value of PA state, the most significant bit of the present state. Output B is also assigned the value of PA state. This confirms the result of the output equations uh, from the previous page, where both A and B equaled PS2, which corresponds to PS state in the Verilog. The Verilog code for calculating the N state based on inputs and PS state is not fully visible in the excerpt, but the presence of the PS state and N state suggests a standard state machine implementation where the next state logic would be defined elsewhere in the code. Here, there are some limitations, which is fixed capacity limit. The system is limited to 9 cores due to the 4-bit counter limit. Here is sensor dependency. Accuracy relies on entry and exit sensor, making the count vulnerable to sensor malfunction or noise. Lack of error detection. No way to detect or correct counter errors from missed or false sensor triggers. No memory. The system loses data if power is disconnected. 555 timer limitations. Display timers have no enable control and a fixed blinking rate determined by components. Here are also modifications that are suggested. Use higher bit counters, integrate a microcontroller for more flexible control, add enable or reset input logic for 555 timers, use multiplex displays. Impact of scaling. So, more bits in counters increase flip-flop count. The FSM becomes more complex. Timer and display logic needs to support greater resolution, and state handling requires power supply adjustment and logic gate expansion. Thank you all.